Okay, good morning, everyone. I hope you guys had a nice Thanksgiving break and you are ready for the last 3 weeks of class. So, as I said before, those last 2 weeks for us are going to be very important. It's going to be the basis for your Calculus 2. So if you mess up now, you will not start Calculus 2 on solid ground. So please work hard with me those last 2 weeks so you can start Calculus 2 very strong. So I'm going to start by recalling what we did last time, and then we generalize the idea of area today. So we talked about the notion of area under the curve. Let's see what was the idea. So you guys have the notes for this, so I'm just going to review it with you. So suppose you have the function f of x equal x squared. So that's f of x equal x squared. And so this is the graph. And I'm interested in the following thing. I'm interested in the area under the graph for x between 0 and 1. So I'm interested in this region R, the area of that. Now, the problem with this function, as I said before, that it's curving. And it's this curvature of the function that make finding the area problematic. Okay, if the function doesn't curve, means if the function is a straight line, okay, that's easy. The area is the area is very simple. The problem that it's curving make it problematic. So how are we going to take care of this problem? So the idea is okay, I cannot find the area of that, so I'm going to approximate it by the area of object that I know. And those objects are going to be actually rectangle. So we're going to do it the following way. We're going to fill it with rectangle. What type of rectangle? We have a lot of choices. The first rectangle we did is what we call right rectangle, and the more mathematical word is right Riemann sum. It means you're going to use what we call right rectangle to approximate the area. So how do we do it? All right. The first way, we're going to do it using 4 subdivisions. What do I mean by that? I'm going to take the interval from 0 to 1. That's my interval. And split it into 4 equal subintervals. Now, the length from here to here is 1. If I divide it into 4 equal pieces, it means each piece here that we're going to call delta x is 1 over 4. And then I'm going to take the following rectangle to fill up my region. So when I subdivide it in 0, 1 into pieces, these are the end point of my intervals. I'm going to fill it this following rectangle. Okay, I'm going to take this first interval. I take its right point. That's where the right is coming from. And I take the rectangle whose height is the value of the function here. And the width is delta x. So the height is the value of the function here. The width is delta x. So I take this as my first rectangle. Now the area of this rectangle is the height. But the height, so that's the area, the height times the width. So the height is the value of the function here. It's from here to here. So it's the value that the function take at 1, 4 times the width, which is delta x, the area of my first rectangle. Okay, so this is right here. That's the area of my first rectangle. I'm going to add to it the area of my second rectangle. Now my second rectangle is the following. It's the rectangle whose base is delta x, base width, and the height is the value of the function here. So it's the value of the function at the half times the width or the base, which is nothing more than the delta x. Plus, I keep doing this, the value of the function at 3/4 times the delta x plus the value of the function at 1, right here, times the delta x, which is going to give me my last rectangle. So these are my rectangles. So that's my first approximation. And then I say, okay, what is f at 1, 4? What is f? F is, this is f of x. It means take input x and square it. So f of 4 is 1 over 4 squared times 1 over 4, 1 over half squared times 1 over 4, 3/4 squared times 1 over 4 plus 1 squared. height, width, height, width, height, width, height, width. Okay, and then I evaluate this. I got a number. And then we said, you know, this is not great because this is not actually the area. There is so many extra pieces in here. So to get a better approximation, we say, okay, let us start taking a smaller rectangle. What do I mean by smaller rectangle? It means the base is actually smaller. So I can fill this area better and better and better. So I said, okay, we can do the same thing. We take 8 subdivisions and we do that. But the principle is the same. So my first rectangle is going to be this one. My second rectangle, third, fourth, and so on and so forth. So the area of the first one, so my delta x is 1/8. So if this is 0, this is 1/8, 2/8, 3, 4, 5, 6/8, 7/8, and 1. The height is the value at 1/8 times delta x, plus the value at 2/8, plus etc. And the last one is the value at 1 times delta x. Now I do the same thing. I substitute, I get this number. It's better than before, better approximation, but of course it's not great. All those pieces here are extra. So those are more than the actual area. So the idea is, you know, you can keep taking more and more subdivision. Means you can take the number of subdivision larger. You can take n to be 10, 100, 200. And as we did last time, there are a lot of computer algebra systems that they can compute those sums. So and the idea is, as n, now n here will represent the number of subdivision. So R4, 4 represent how many subdivision? R8, 8 represent how many subdivision? So as n will represent the number subdivision, gets larger. Rn, it means the sum of the area of the right rectangle become closer and closer to the area under the curve. Okay, and last time I gave you like the numbers. So this is Rn. When I take 8 subdivisions, I got 10 subdivisions, 0.85, 20, 0.35, 100, 0.33, 500, 0.33. So those areas are getting closer and closer to 0.33. If I take more and more, we realize it becoming closer and closer. Okay? So this is right rectangle. Now then the idea, you know, why did you take the right end point? You can take, you know, the left end point. And we did that. So we're gonna review it again quickly. So approximate the area using left Riemann sum. Left Riemann sum, it means you're gonna take left rectangle. And what do we mean by left rectangle? It's the same idea. We're gonna do that with 4 subdivision. We divide our interval in 4 equal subinterval. The length of each one is 1/4. And then I start focusing. Instead of taking for height the value at the right point, I take for height the value at the left point, which happened to be 0 there. Then so that's my first rectangle. It's just a straight line. Then the height at 1/4 times the base. Second rectangle. The height at 1/2 times the base. Third rectangle. The height at 3/4 times the base. Fourth rectangle. In this case, of course, the sum of the area is less than the actual area, but we're doing the same type of approximation. And then I compute L4, which is f of 0 times the base, plus f at 4, the output at 4, times delta x, the output here, output at 3/4 times delta x. And I do exactly the same thing. So now, as n, the number of subdivision. So n represent the number of subdivision gets larger. The left sum become closer and closer to the area under the curve. So we can use either the right endpoint or we can use left endpoint to approximate the area. But then there are other approaches. Actually, there are millions, tons of them, and I will mention that. Then there is the idea of using the midpoint to approximate the sum. And this I left it open because I want to make sure we understand clearly what the midpoint sum. So let us remember what the midpoint sum is. Again, the same idea. We divide the interval into 4 equal pieces. But then what we're going to take for height? Left Riemann sum we took for height the value at the right point. The right we took the for height the value here. For the medium we took for the midpoint we take for height the value of the function right stuck in the middle, this point. So this point, this point, this point, and that's my height. My height is from here to here, but my base do not change. So that's the base. The base does not change for all of them. It's the height that it is gonna change. Sorry, it should be lower. I will cheat. Okay, right here. So that's my first rectangle. The height is the value at the midpoint. The width do not change at all. That's my delta x. So that's my second rectangle. That's the height. And that's the height right there. Okay. Now to be able to find the sum of the area of those rectangles, I need to find the midpoint. So I can evaluate the function. So I need to find this point, that point, and that point. So let's find them out. This is 0. So this one I'm going to do it just by looking at the picture because it's not hard. This is 1/4. The midpoint, this one should be 1/8. Okay. Now what should be this point? Now you guys start helping me with that. What should be the point right here? Quickly. It's 1/8. What should be this one?
3/8.
3/8. Quickly, that one.
5/8.
5/8, 3/8. For we're adding, 1/8. Then, so right here I have 3/8, 5/8, 6/8, 7/8. Crucial point. Otherwise, I cannot really approximate the area. So what is Mn? Mn is, watch, the value at the midpoint times the base. Okay. Plus the value at the midpoint, 3/8 times the base, plus the value at 5/8 times the base. Height, base, height, base, height, base. Very important to keep it for repeating it for yourself because it's a sum that we have to basically memorize. Okay, now the rest is simple. What's f of 8 is the output at 8 in this particular problem. And then the output at 8, and so on and so forth. And the last one was 7/8 squared times 1/4. And then I add them. And I add those numbers, I get 0.328. Okay, so that's what's for subdivision. Now the midpoint is definitely a better approximation. Just we look at the picture. If I think a little bit about this piece here, the rectangle, I have this extra. And the actual area, we're losing that. So we're almost compensating what we're losing. So we can actually prove it that the midpoint is a way, way better approximation than the left and right point. But eventually, theoretically, sometimes we use any sum because all of them eventually, whether I use midpoint sum, left sum, right sum, when n is large, all of them will become close to the actual area. And that's really the most important idea. Okay, so now again, when n becomes large, it means when n represent the number of subdivision becomes very large. Also, the mn, it means m10, m100, m500 become close to the actual area under the curve. So they all become close to the actual area. Okay. So this example. Now we're going to introduce some notation to generalize the idea of the area. So we're going to use notation in general for left sum, right sum, and midpoint sum. So right now what we're going to do is the general idea. So right there, left, right, and midpoint Riemann sum. Okay. let f of x be a positive function. Now, why did I actually ask f to be positive in today's scenario? Tomorrow's scenario, I'll remove positive. Well, f is positive because if you go back here, if when I evaluate f at 1,4 times delta x and get the area of this piece, my function f is negative, I'm not going to get the area, okay, at least for now. So if my function here is negative, suppose this is my function right there, go up. Suppose this is 1/4. If f at 1/4 is negative, f of 1/4 times the width will not give me area anymore. Actually, it's going to give me minus the area. Something I look at tomorrow. But for today, since I'm actually talking about area, I'm not changing the meaning. Area is area. So if the function is negative, I cannot call f at 1/4 will not represent the area. So I'm going to put the condition f of x positive. And tomorrow I will remove it, but I will explain what is the situation. So let f be a positive functional interval AB. I'm trying to define in general left, right, and midpoint Riemann sum. We're going to take the interval AB and we're going to divide it into n equal subinterval. Okay? We're going to call delta x the length of each subinterval. So that's the picture right here. That's my function. I'm going to divide it into n equal subinterval. I'm going to call delta x the length. So what is the formula for delta x? Is equal to what? This is the general setting. If I take this interval and split it into n pieces, that's going to be the length of every piece. Who can give me the formula? And then we talk about it. In general, I'm doing the general setup now, which is important. Anybody can give me a formula for delta x? Okay, anybody else? So let's think about it. How much do we have from here to here? How much do we have from here to here? What's the length of this interval? This interval, what's the length of it from here to here? This is B, this is A. The length from here to here is B minus A. Okay? If I divide it into n equal pieces, so from here to here I have B minus A. If I divide this into n equal pieces, each one of them will be B minus A divided by n. So basically, suppose my B and A, so that's the idea. Suppose this is 4 and this is 10. So the length from here to here is definitely the 10 minus 4. If I divide it into 100 pieces, each one of them is going to be 10 minus 4 divided by 100. That's really what I am talking about. So delta x is, so my delta x is B minus A over F. Okay, as I said, we're trying to do the general. So we take delta x, the length of every subinterval, then delta x is B minus A over F. Now, we're going to call x0, x1, x2 through xn the end point of the subinterval. Your book is using, actually that's the first book, the first time I see that, the book is calling them grid points. Okay, so if you see grid points, it means they are talking about the end points of the subinterval. Again, what do I mean by that? Okay, go back to here. X0 is, what's the end point? I mean, these are my subintervals. And so on. I have n of them. The grid are, this is, A is x0. Okay, so as I said, we're building notation, which is going to become crucial. This is x sub 1. Okay, so, and this is x2. That's what we mean, the end point of the subinterval, or what your book called grid points. This is x3, and so on and so forth. So this is, the last point is going to be xn, and the point before it is going to be x, and the subscript is n minus 1. Okay, that's the notation. x1, x2, x3, x4, etc., xn minus 1, and this is xn. Okay. So if I divide into 100 interval, so this will be x0, x1, and the last one will be, of course, x100. That's what I'm talking about. And this is going to be x99 if I divide into 100 interval. Right. Okay. Now, the notation for left sum, right sum, and midpoint sum. The general notation, actually, or I'm going to call it the sigma notation. So what was the left Riemann sum with n subdivision? It's exactly what we did. The only thing I'm adding now are the notation. So what is the left sum? Left. Left, it means we divide it and we take for height the value at the left endpoint. So the left sum is, once you understand what it is the area here. And remember, this is going to become x1 plus the area here. Usually I like to do it this way. This is x2. Now, of course, I have n of them, and I don't know what n is, because the goal now is really to build up the general notation. And this is going to be x3. And etc. You know, I'm filling it, but I have n, and I don't know n. I'm just going to work on the last two. And the idea is that you keep doing this. So if this is xn minus 1, what's my notation? That the last rectangle is going to be the value of the function here times the width. That will be my last rectangle. And that's the one before it. And here also we're filling it, but I don't know how many. So we keep filling it, but I don't know how many because n is in general. Very good. Now, what is Ln? Ln is the sum of the area of the rectangle in the picture. Sum of area of rectangle. Basically in the picture. That's the easiest way to explain it. Okay, now we're going to write it. The sum equal to, again, the picture. But I have to use notation. It's the value of the function at the left point, x0, times the delta x. Okay, so this here, that's the area is f of x0 delta x plus the area of that. This is f of x1 times delta x plus f of x2 times delta x plus etc. What do I mean by etc.? I mean, there are more rectangles, so I'm not going to write all of them because it's actually, I don't know how to write them. N could be 100 or 1 million. I don't know what N is. But what's going to be the last term? What's going to be the last term in this sum? Who can write it up for me? What's going to be the last term in this sum? Using the notation. What's the last area? That's the last area. So it's going to be the last term. The value of the function here, that's the height. It means the value of the function at x n minus 1 times the width, delta x. So that's going to be the general formula of the sum. Now, we're going to use sigma notation to rewrite the sum. Okay, we're going to use sigma notation to rewrite the sum. So let us see how we're going to use the sigma notation. So that's going to be written sigma. Sigma. That's the sum sign, sigma. What's changing in this picture? Let's see what's changing. What's changing is this index. I have x0 here. I have x1. I have x2. I should have x3 here. Those are what's changing. And here I have xn minus 1. So in sigma notation, we're going to rewrite this the following. We're adding quantities of this form. The value of the function at x, watch carefully, I'm going to write it, certain xi times the delta x. Okay, and my I changes from 0, that's where it starts, and the last value it takes is n minus 1. And that's the left Riemann sum in sigma notation. Absolutely crucial notation. Okay, so what's the left Riemann sum? It means we're adding what? If I is 0, remember how we did. If I is 0, it means I'm taking f of x0 times L delta x. Plus, if I is 1, f of x1 times delta x. I is 2, f of x2 times delta x. N, the n here in the top, which is very confusing for us, n represent the number of subdivision. In how many ways, how many subdivision we did. So if we subdivide the interval into 100, it's going to be from 0 to 99 because we're taking left point. So the last point here is not going to be the value at xn, it's going to be the value at xn minus 1. So that's the sigma notation for the left Riemann sum. We're going to do that for right Riemann sum and midpoint sum. Okay. Now for right Riemann sum, what's going to be in sigma notation? So let us remember the difference. The notation are the same. That's x0. This is x1, x2, and this is x to the n minus, sorry, this is xn. That's the last term in my sum. And what's the right sum? Once you know the picture, you know what you're doing. The value of the function at, so this is my interval, is the value here. The value here times the width. That's my first term. The value at x2 times the width, and so on and so forth. The value at x3 times the width. This is x3. And then the value at xn times the width. That's the last rectangle. And the one before it should have been this one. And etc. Okay, so we have a lot of them. We have n of them, and they fill the curve. But so now what is Ln? Rn. Rn is the sum of the area of the rectangle. So let's write Rn carefully. You don't memorize it, just remember the picture. It's the value at the function at x1, that's the height, times the width. Height times width, area, plus height times the width, the area of the second one, plus, again, I keep going, but that's why we introduce sigma notation, so we don't have to keep writing. But for now, I'll write a few more terms, plus f of x4. So I keep adding. Now, what's going to be my last term in this picture? What's going to be my last term? It means what's the area of my last rectangle? I think you should be more ready to give me the answer now. Who would like to give me the last term in my sum? Anybody? F of xn, exactly, because that's the height this time, and that's the width. So the last term is going to be f at xn times the width, delta x. Okay, all right. What's going to be the term before it? Just to make sure you guys understand the picture. What should go here? Each one of you should be able to tell me. What should be the term before, just out of curiosity? What's going to be the term before it is the area of this rectangle. What's the area of this rectangle using notation? The whole idea now is notation. It's xn minus 1. Absolutely. It's the value of the function at xn minus 1 times delta x. Right? Now, in sigma notation, because that's really the idea now, is start interacting with the sum, what we call Riemann sum. So that's left Riemann sum, right Riemann sum. So in sigma notation, so now we're adding. Now when we have sigma notation, we have to think what's really changing is the sum. What's changing is the subscript of x. x1, x2, x3, x4, it depends on n, xn minus 1, xn. So what we are adding, so that's what's changing. So something of the form. The value of the function at xi, that's what's changing, times the delta x. And my I this time. Start from where to where? It starts from, what was the first one? It's this area of this rectangle, which is it start at 1. So it changed a little bit notation. And the last one is, remember, n is the number of subdivision. That's what the n represents. The n is the number of subdivision. Okay, so that's left Riemann sum, right Riemann sum. And now the notation for midpoint sum, which is actually the same idea, but instead of taking x0 of x1, we're going to take the point in the middle. So notation.
I have a question.
Of course, go ahead.
Why does right Riemann sum and left Riemann sum have different start points and different endpoints?
Let us think about it, okay? This is the picture for left sum, right? What is the first rectangle? What's the height of the first rectangle? Are you with me?
Yes, wouldn't it just be x over the, well, x times the height?
What's the height here?
Wouldn't it be just x put into the function?
I don't have the, yeah, but which x should be put into the function?
X of 1?
No, not the left one, no.
Oh,
Because,
x of 0.
Right. Are you seeing? F of x 0, because I'm taking left. You times it by what? Delta x. You follow me?
Yes.
What about the right one? What's the first rectangle? What's the area? What's the height? The value of the function where?
X of 1.
X sub 1. That's the height. So in my sum here, what should be the first one? F of x sub 1 times delta x. What should be the first term here? F of x0 sub times delta x. Do you see why I'm starting at 0? Because my first rectangle is not f of x1. If I start at 1, it means I'm telling you my first rectangle is f of x1. No, my first rectangle is the value of the function x0 times the delta x.
Okay.
Now, why n minus 1 here and why n here?
Is it because the second to final,
Right.
The starting points of the last rectangles are different?
Absolutely, because here, what's the last rectangle? It's the value not at xn. It's the value at xn minus 1, because it's the left. That's the height, and that's the width. So my last one is f of xn minus 1, not at the end point, at the last point. It's at the point before it. So my sum will have to go to here. Right here to n, because my sum right there, the last rectangle is the value at xn. for height, and the width is the delta x. Does this make more sense?
Yes.
Okay, very good. Now,
Thank
midpoint.
you.
Oh, sure, midpoint. The same idea. Okay, so the goal today is really start introducing you to those notations that are absolutely crucial for us. Okay, now the last point is the midpoint. Midpoint, Riemann sum with n subdivision. Again, where my goal now is just to explain the notation more than that. But let us remember the picture here. For the midpoint, what do? I take the interval, but then I focus on the midpoint. That's the midpoint. And I take for height the value here, that's my height. And the width, the base is the same. I don't change the same, it's the base. So this is my base. So this is my first rectangle. So this is my first rectangle. Okay, so I need to give a name for the midpoint. So we're gonna call it x1, and I think the book is using star. So we're gonna call it x1 star. I need to give that a name. Otherwise, I cannot tell you, I have to tell you what's the height. So it's the value here. And then we kept doing the same thing. So we focused on the midpoint right here. And then I took this for height. And I take this for width. That's my second one. And I'm gonna give it a name, the same thing. It's gonna call it x2 and star, okay, for the midpoint. And then I keep doing it. So I keep repeating myself, but now the idea is to cover it with more and more rectangle. So that's the height and that's the base. So that's x3 star, which is halfway through. And then I keep doing the same halfway to the last one. And the last one is going to, that's the height. This one will be xn star. That's what it will be. That's my last rectangle. Okay. Now there is a formula that will help us to compute the midpoint. I mean, you can either basically, for the midpoint, you can either look at them and just say, okay, what they are, spot them, or there is a formula. And the formula is this. x1 star is just the midpoint. Now there is a formula, you see it in high school. The midpoint between the first and this is usually x0 plus x1 over 2. I mean, that's how you find the halfway between 2 points. And x2 star will be, so to find the halfway between those two means you average the end point. So it's going to be x1 plus x2 over 2, and so on and so forth. So you can use this formula to find the midpoint, or honestly, if it's an easy problem, you can just look at it and figure it out. So what is Mn now? Now we're going to repeat the same thing. Let's see what Mn is. Mn is the value of the function at the midpoint. So it's going to be x1 star. That's the height. The width is the same. Okay, plus the value at the midpoint times delta x. Plus, and we keep adding. So those 3 dot dot means that you keep add and add. So my last rectangle is star times delta x. And this is just a formula to find the midpoint. It means it's just the average. So the midpoint here, you take the coordinate here, the coordinate here, you add them, you divide them by 2. That's really the formula. Midpoint here, you take those 2 points, you add them, and then you divide by 2, and so on and so forth. So that's the formula for the midpoint. Now in sigma notation, that's the sigma notation that trying to build up. C equal to sigma, again, f of x star I this time, because that's what's changing, times, so that's the height, times delta x, that's the base, and my I go from 1 after my notation to n. And usually the x star I is the midpoint. is the midpoint of the interval. So xi minus 1 xi. So it's the midpoint, halfway in between. Okay. So that's the notation for the midpoint sum. All right. Now back to the area under the curve. And again, today is a lot of notation, but absolutely we need those. You have to start building a feeling for them. Now, area under the graph, and we're gonna give a notation for, not notation, we're gonna write mathematically, what do we mean by the left sum, right sum, midpoint sum become very close to the area. So mathematically, how do we write this in a correct way? So area under the graph. So suppose f of x is a positive function. Okay, that's my function. My function is positive. I'm going to talk about the area. And what is the area under the graph? So we know that it's problematic because it's curving. So we don't know what the area is. So we're going to give it, the way we're doing it is by approximating it. By left sum, right sum, midpoint sum. That's what we're doing. So what's the area under the curve? And now you have to watch carefully what I am going to do. Okay. If I go back to my first problem, what's the area under the curve? What did we do? We took 10 subdivision for each one of them. So I can focus on this one, for example, the left sum. We took 10 subdivision, we evaluated the area. Then we took more subdivision, we evaluated the left sum. Then we took more, we evaluated. Then we took more, we evaluated. And then what's the idea? We said we keep taking more and more sums. So I can take like 1,000 and evaluate. Now I take 1,000,000. And as you realized last time, I was able to do it using computer and I evaluate. And the more n I take, the more subdivision I take, the closer I get to the actual area. The more subdivision I take, the larger the n, the closer I get to the actual area. So how we're gonna define this idea mathematically is that the larger n gets, the closer you get to the actual area. So how we're gonna do that mathematically? So this is the notation. So the area under the curve is basically, I'm gonna write it in word, then symbolically. It's what happened to the left sum or the right sum, but first I'm gonna write sum. Is what happened to the left 3-month sum. So this is not the definition, it's the idea. It's what happened to the left 3-month sum when n get larger and larger. When n gets larger and larger. Or the right 3-month sum, but now I'm focusing on one. So the area is the left 3-month sum when n gets larger and larger. What does n represent? N represents the number of subdivisions. Okay, so what's going to be the area? Now a more formal definition. Equal to. What's the left 3-month sum? In notation. Notation is, this is the left 3-month sum. It's the sigma of f of xi times delta x. So that's the left 3-month sum. I equals 0 to n minus 1. Okay. But now, so that's the left 3-month sum. So if I have 100 subdivision, it's from 0 to 99. If I have 1,000,000 subdivision, it's from 0 to 1,000,000 minus 1. So that's really what the left 3-month sum. But now, what is the value of n? N gets larger and larger. Mathematically, we're going to write this is the area to be those sums, but when n becomes very large. Mathematically, we're going to write this as the limit as n goes to infinity of that. Okay, so watch carefully. N, remember, n here is the number of subdivision. So what's the area under the graph is? If you take those sum, what does mean n limit as n goes to infinity. It means what happens when n becomes larger and larger. So I cannot tell you take n to be 1,000. You tell me, but you get better approximation when n equal a million. I cannot tell you n equal a million because you tell me you get a better approximation if n is larger. In math, we have to give definition. So definition is you compute those sums for larger and larger n and realize what they get close to. So mathematically, it's the limit as n tends to infinity of the left Riemann sum. So the area is what happened to those sums when n becomes very large. Remember this n here and the n here. This n is the number of subdivision. That's really what my n is. Now, there is no reason we can use the left sum. We can use the right sum. They all get close to the same value. So I can say here is the same thing of, so it's equal to, now I'm gonna write right sum here. The right sum will become the same thing, it's sigma I equal, for the right, we start from 1 to n, f of xi delta x. So this is the right sum. But then we let the number of subdivision gets larger and larger. Gets larger and larger. That's really what n is. It means the number of subdivision becomes larger. Equal to, so that's the right sum here. Right Riemann sum. And finally, or I can use the same thing as the midpoint sum, which is the following. The limit as n goes to infinity. I know there is a lot of notation today, a little bit more tomorrow, but they are crucial. I have no way out of those. I equal 1 to n, but this time the height is the value at the midpoint times the delta x. Okay, so height, width, height, width. We were adding the height times the width, and that's the midpoint. Okay, and regardless which sum we take, when n becomes large, all of them will become close to the area. The midpoint sum get close to the area much faster than the other two, but all of them get close to the area when n is very large. Okay. Let me ask you a very just for my own peace of mind. When n becomes very large, what happened to delta x? What happened to delta x? Back to you.
It approaches 0.
Absolutely, it becomes very close to 0, and that's really what we want. We want really to fill those rectangles, this region, with very, 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 very tiny rectangle. I mean, very, very tiny rectangle. Okay, so that's really the formal definition of the area under the curve. I know the notation is bothersome, but you have no way out. We have to get used to it. Okay, so this is left Riemann sum. N goes to infinity, reflect the idea that I want the delta x to become very, very small. Otherwise, I'm not filling it correctly. So delta x goes to 0 or n be very large. Those are exactly the same. I reflect the same idea. So it's what happened to those sum when n is very large. What happened when n is large? What happened when n is large? So this n here is this n here. The I is because we're adding rectangle. Okay, so that's the formal definition of that. Now I finish with one more example, and then the idea hopefully will become very clear and we can go tomorrow. So my last example, I will do, instead of doing all the sums, I'm going to do one because I only have a minute. So here's the question. Estimate the area under the graph of the function f of x equal x squared plus 1 on the interval minus 1, 2. Okay, and that I say using left Riemann sum. Right? Usually I don't memorize any formula for those particular problem. I just remember the picture. Once the picture is clear in my mind, I will proceed. So first we graph, because, so this is really the graph here. f of x equal x squared plus 1. That's my function of interest. So this is, and my interval is -1 and 2. Okay, so this is my function. So it is goes like that. Here, that's a parabola. So it goes like this and goes like that. So that's really my function. And so this is -1. I don't care about that piece. And this is 2. So I can erase this piece. I don't care about it. And I can erase that piece. And basically, I'm interested in this area. Okay, f of x equal x squared plus 1. So this function here is f of x equal x squared plus 1. Right? I'm going to use left Riemann sum with n equal to 6. N equal to 6, it means I need to divide this interval into 6 pieces. So let's see what's the delta x here. All right, what's the length from here to here? You can use the formula b minus a, or you can actually just divide it by n. I'll use this formula for this problem and then I'll stop. So b minus a, b is 2, minus a is -1, so it's going to give me 3. My n is 6 equal a half. Okay, basically it's this interval. It's 3 units. You divide into 6 pieces is a half. Okay, so this is my delta x. Now it means I have to divide this. So this is my subdivision. So these are the subdivision. These are the x1, x2, x3, and x4. So first let us find them. Otherwise, we're in trouble. This is x1, my x0, -1. If this is a half, so this is going to be, of course, that's a 0. This will be minus a half, and that would be a 1, 3/2. So these are the x1, that's x0 for me. That's the x1, x2, x3, x4, x5, and this is the x6. Okay, left Riemann sum. Very easy. As I said, it's the picture. It means you're taking the value of the function at the left point times that, plus the value here. So that's my first rectangle. My second rectangle is this one. Then the value at 0 times the delta x. Third rectangle, the value at a half times the delta x. My rectangle, the value at 1 times the delta x. And finally, my last rectangle, because I'm taking the left sum. Okay, so these are the rectangles. Now, the left sum, so I need L6. Again, I look at my picture and I proceed. As you realize, I'm really relying on, so the area here is the value of the function at -1 times the width, that's a half, plus the value at -1/2 times a half, the value at 0 times a half, the value at a half times a half, plus, I'm looking at my picture and that's how I'm writing everything, plus my last one is at 3/2. Okay, that is equal to. Now, what's f of -1? F of -1 is the output at -1. My function is x squared plus 1. So f at -1 is nothing more than the output, means -1 squared plus 1. That's the output. F of -1/2, that's the output, times a half. F of 0 is the output at 0, times a half, and so on. So it's a half squared plus 1 times a half. It's a 1 squared plus 1. Always think of the picture, so never lose track of what we are doing for now. Plus 1 times a half. And the rest is just picking up your calculator, or if we do that, we will get 5.3, how much? Okay, 375. That's that. Okay, so that's the approximation. Now, of course, time is up, but since your problem will also involve your homework midpoint, let me make sure we all figure out the midpoint. I will not compute it. I will just want to make sure you know how to find the midpoint. Okay, so you help me out. If I want the midpoint, means I want those points. I need those for height, because this will become the height. That would become the height. That's the midpoint. That's the height. That's the height. Okay. All right. We can figure out the coordinate of the midpoint. So that will become x3 star, x4 star, x5 star, x6 star. All right, what is x1 star? You can figure it out just by looking at it, and then I will tell you exactly, the formula. But remember, it means every interval is 1/2, right? So what's going to be this one?
-3/4.
-3/4. Do you agree with him? Because this is 1/2 divided by 2. So every piece here is 1/4. Every piece here is 1/4. So you can spot it and figure it out. Or if you can't spot it, which I doubt you want, you can use the formula. x1 star is the midpoint between here and here. How do you find the midpoint? You just add, it's -1/2 minus 1 divided by 2, which is -3/4. So you can either spot it or you can just use the formula. And then x2 star is easy. x2 star is -1/4. That's 1/4. That's going to be 3/4. And then you're adding 1/4. 3/4, 4, 4, 5, 4. You're adding 1/4 each time. 6, 4, 7, 4. And then you can prove the midpoint. All right. Okay, I think you are very much ready for your homework. As you guys know, your exam was graded, and please, your final is in 2 weeks. Exam 3 will be very much on your final. Come to my office hours, as I wrote on for some of you, and ask any question you want about the exam, and I will be very happy to work with you on it. Okay, all right. Good luck, and please do your homework for tomorrow, and bye for now.